talk about, today we will take a look at the concept of convolutional neural network. Convolutional neural network is a type of neural network that allow you to analyze the spatial data. If you have the data that in spatial domain that have certain redundancy, that they are kind of each of the data points that are nearing, like between or near one another, have certain correlation, have certain redundancy. You may want to have a way that summarize those data together, so that the network would be able to detect particular patterns out of those spatial data. Convolutional neural network would come into play in allowing you to perform such a task. We will take a look at that today. So let's begin. All right. So this convolutional neural network is a type of architecture, a type of network architecture that allow you to perform analysis of grid data. Grid data are the data that are like image or sequence of data that can be drawn into a grid, right? Into a grid data that look like this, something like this one, the grid data. Okay, this grid data can be analyzed using the convolutional neural network through the process of convolution. This process of convolution would allow us to learn what would be the best filter, what would be the best kernel that would process this grid data. Okay, such a way allow the implementation of convolutional neural network allow us to process either both the 1D data as well. Like this is like an image 2D data, but we can also do the use convolutional neural network to process the data that is in one dimension by having something like a grid that would move along the direction here. Right? So this grid would, this mass, this kernel would move along the axis that we want to analyze. For the image, it would be done so in this manner, like we would have like a grid image like this one that move in the picture. Right? You may have seen that I wrote it on the right hand side and moved to the left, but it doesn't matter, it can move on the other way as well. Right? So the name comes from the process of convolution, borrowed from signal processing. Some of you may have learned that in the signal system course here at CPE. Some of you may have not, but you may have took image processing and learn about filter, that you can create a filter to do edge detection or blurring in the image processing course. Convolution is a type of filter as well, that you can think of a mask that or a filter that is learned through this process to represent the pattern of data that the system has learned. So the process, the operation convolution is a special kind of linear operator. It's a linear operator that like it would go through your data, perform convolution so that you have another pattern detected data, derived data, like it can be the edge that are detected, it can be the part of the images that are detected. Okay, so this is the idea of convolutional neural network. But what is convolution? Convolution operator, or in short convolution, can be mathematically defined as this equation. Usually in signal processing, we use convolution of process to represent the system in time domain. That is, if you have a certain system represented as an impulse response, you can represent the results of that impulse response when you give the X input to the systems, so that it will produce Y output. The process of producing the output is the convolution process. If you represent the systems as impulse response, that is in signal processing, right? But in order to make this simpler, right, I would like to talk about convolution here as just sliding window. That is, you have a window, and then you slide this window around in order to make calculation. For example, for this 1D calculation, we can think about convolution as having a data, one-dimensional data set as an array, and then you create a types of mass over this array. The idea of convolutional neural network is to learn the one that I highlight here. Learn values of this mass. The value of this mass would be learned that on what types of value would allow the system to best performing that job. That job can be doing classification, doing regression, comparison, which we will see later on in different application on different architecture, right? So this mass would have to move. Okay. So how does this represent? Be represented in the mathematical formula of operation here? We have this x, because once you have the mass, you have to multiply the mass with the data, and for each multiplication, you need to perform summation of the data that are resulting from the multiplication, right? To get the value of results at specific point. So this is like your x, this is your y, and then to make it well represented here, let me erase it and then write it as s instead. Right, so and then we have this w that we move around. Okay, so each multiplication results and summation results in just one value. And from this, you can see that the operation of multiplication and summation can be represented as an equation like this one. This equation, you have a signal x or a data x, and the data x is multiplied with the flipped version, right? Because you can see that there is minus a there on the a axis, the difference in a axis. The flipped version of the window function, and sliding by the shifting by t here. So think about t as the shift, and then just that. It's the shifted version of w. So that means as t change, the window will change, and once the window change, you multiply it with the data, and then you get the aggregated sum. This is the aggregated sum, sigma here, of using that mass on certain part of the data. This allows us to let the system summarize certain features in the data, right? So by learning the filter here, it would allow us to do different things. For example, if the filter looks like this, say it's 1, 1, and 1. If the filter look like this, you have all the value equal 1s. What does it mean, right? And then multiply by 1 over 3, say 1 over 3. This would mean the results should be the blur version, right? The low pass filter version of the original version of the signal. That means in order to perform classification of such a task, you need a low pass frequency version of the data out. On the other hand, if the mass that is learned looks like this, minus 1, 0, and 1. If the mass looks like this, it means that what you are trying to detect is actually the change, because this mass would try to detect the change in the data, the change upward in the data. If there is like minus 1, 0, and 1 event in the data set, it would be able to detect that data out. So you can see that from the mass, it can be configured to do different types of filter. Convolutional neural network ideas are to learn this mass, are to learn what should be the best representation of the mass that would generate the data, the process versions of the data out. Right? So this is the idea. Right? This is a convolutional operator. Let's take a look at when you have 2 dimensions. That might allow you to gain the understanding more. Now let's define some of the terminology of the terms here. Let I be the input data, the multi-dimensional array. K here is the kernel or filter, and S is the feature map, right? Let me draw it here. Okay. Let me show this a bit. We have the data here, input data, the grid data as I, and then in this grid data you may have this small mass. We call this a kernel, or you may call this a filter to be learned. Right? So the weights in convolutional neural networks are the weight of the mass, right? And then by convoluting this mass, right, moving from left to right, top to bottom, moving around, this would generate through convolution. This would generate another image with a similar size, right? We call this a resulting feature map or output. Okay, feature map would be different depending on the mass, depending on the kernel. Okay, but we don't know what types of feature map that are required. We would let the system learn, right, what type of feature map they would need, right, what type of features that they would need in order to perform the task. But the system has to learn it through learning the kernel function, through learning the filters, right? So you can see that the idea is like it's a bit two-step back. That is, instead of learning map directly, you are trying to let the system figure out what type of suitable learning map or intermediate data should be by learning the processing function, by learning the kernel that would process the data. Right? This is the terminology. Let me move on. Sure. All right. Let's take a look at how the 1D convolution works. Right? 1D convolution, when you have a mass in the red moving along the data, it would perform the multiplication of the mass with the data and summarize the area under the curve of the resulting energy. Right? Sometimes this is called energy because you're kind of trying to detecting certain overlapping or certain energy of the function. So let's take a look at this again. Once the mass overlap with the signal, you can see the rising in energy, and then once it's passed, then it would decrease, right? Because the overlapping part decrease. Okay. This is 1D convolution. Just multiply and sum. Right? Actually, if you learn it in the signal system term, there is a process of shift, flip, multiply, add. Right? And if you were to go back a few slides, you'll see that there's a flip, which is not important here because mostly the mass will let it figure out that way. But there is a shift process, and then multiplication and summation. You can think of multiplication and summation together as the dot product. Right? You are trying to calculating the dot product between the mass and the data to see the projection of the data onto specific data plane. That is learned through kernel learning. Okay. This is 1D convolution. 2D convolution is done by learning the mass, like learning this mass. Right? What types of values this mass should be. Once learned it, right, you can use the mass to multiply to the data and then summarize them, summarize the results to get the results of the specific point. And this mass will move, right? You can see that it moves here in this direction. That's why you get the location of the mass shifted. Now, this is two-dimensional convolution concepts. This convolution is not a new concept at all, actually, if you learn the concepts in image processing. Right? Because for a normal image, let's say suppose you have image of cat. I haven't read this for a long time. Sometimes like this. If you have an image, right, and then you use the convolution filter like this one. Let's say -1, -1, -1, 0, 0, 0, 1, 1, 1. Right. This is, I think, it's called a Sobel filter. Right. It is a filter that would go through convolute through the image, and then you get something like, suppose here there's a certain rendering. Right. The final would be just an edge, underlying edge that is detected from the data. Right. So this is called edge detection in image processing. Right. So this is this technique is quite an old concept. Like if you use Photoshop, you will see that this function has been together with image processing software for quite a long time, and you can define a filter to perform such a task. But let's say now we will not specify what types of operator this should be, but instead we will let the system learn what the kernel should be in order to perform a specific task. So this is quite cool in the sense that it would learn the filter automatically through from the optimization process. Okay. So yeah. Right. So let's revise a bit on a process of convolution. Right. A process of convolution, like I explained earlier, this is the convolution in signal systems. That in order to compute y, you need to multiply x with the shifted version of the kernel, the hn minus kx, and then sum of k for all time. So this is like you have a mask, and then you have a signal, and then you kind of multiply the signal with the mask, and then sum of all time to get one value at that location, at that n. Right? So that you get the results at the time of n. Okay, this is the convolution process. Right? The convolution process on each step consists of running. This is the running sum that you want to aggregate the data together at the time n. This is the results of reverse minus k here, and then shift n here, and then multiply with the signal, and then sum of all k of all time. Okay. Now let's take a look at how it works in calculation. Suppose I have xn that looks like this. We have this delta function as an impulse. It means that it would have just one value at that location. This delta n minus 1 it means that you have the value equal 1 at a time minus 1. At a time, this is x equal, x would be like this one, x equal minus 1 at time plus 1, and equal 2 at time minus 1, and equal 1 at time 0. This is for the discrete value of xn, looks like this one. Alright, and then the step of convolution, and for the hn here, I let it be just the delta n plus 1, which is this bar, and delta n, which is the sample at 0. Okay, just these two. And then let's calculate the convolution process of this. The convolution process consists of the flip version of h, the shift of n, and then multiplication with the actual signal, and then summation of all k. Okay, let's take a look step by step how it works. Okay, first step, hk looks like this. This is hk. Right, hk is minus 1 and 0, and have 2 bar here. The first step is to reverse, because we have h minus k here. Reverse from hk to h minus k. You get the flipped version of the signal with regard to 0 as the flipping axis. That's why we have this k. And then shift for each n. Let's start with n equal minus 2. When n equal minus 2, that means this whole curve would shift to the left by 2 steps. This is n minus 2. Multiply, the next step is to multiply h minus 2 minus k with xk. With xk, this is k-axis. Multiply them together, you can see that there is one bar that is overlapped, which is at the location minus 1. That means once you multiply, the results would look like the right hand side. You have just one bar left. Then summation of k, right? Summation of k for all infinity. Then we have this value equal to. That means at the time minus 2, y minus 2 should equal to, right, from this one we have y minus 2 equals to. Some of you may scratch your head right now and thought that you are over this. You are over this a long time ago, but it's no, no, it's not. So I saw that the voice not clear. Is that right? Is it better now? All right. Okay. So this is a process of convolution, as it illustrated in the signal system concept. Now for 2D convolution, the convolution of 2 dimension. If we take a look at the definition of convolution of 2 dimension, you can see that they are actually the same. This is convolution operator in 2 dimension. The Sij is the result, the feature map of I and j when you convolute I with k of each location. The convolution occurs by multiplying k minus m minus n. Minus m minus n is in the index of m and n, and then for each I here, you kind of think about this way. This is the flipped version of m axis and n axis, and then multiply it with a certain location of data at location I and j. Okay, and then so best way is to maybe to write this down. Right. Let's have defined the first. You have I. Okay, and we have this small mass k. This small mass current location is at I and j location. Okay, and at an I and j location, you shift. You can see that from this, we are trying to multiply kmn here with the shifted location of I and j. Right. So this is like for each of the location, we try to multiply k with that location and then sum them all together. Okay, this is the process of convolution. In image, flipping is unnecessary because usually the grid is symmetric, or if in the case of a convolutional neural network, the grid would be learned. So the proper I would say the usual definition is not required. Okay, now. Right. So in a way, this is the same as calculate the cross correlation. The cross correlation between the two values. This is the equation for the convolution in 2 dimensions. This is the equation for the cross correlation. For 2 dimensions, they are exactly the same in calculation. This is just that the algorithms are similar to one another, compatible to one another, right? So it doesn't matter whether you flip the grid or not. The result will be the same. This picture would illustrate the idea. The idea of convolutional neural network is to take into account, try to capture the patterns that exist in a certain spatial location, right? So for this one, you can see that we have a mass here, a kernel that is learned. This kernel will need to be learned, and this kernel would pass through each step, right? Starting from have a center at this point, and then it would go to this point and this point, and then going down, going to this location, Right. On each of that location, the mass is multiplied with image on the surrounding area. That's why for the first resulting pixel, for the first resulting feature map values, you have the value of A times W and B times X and E times Y and F times Z. Right? This is what is written here. Right? This is the output. For the next one is the result of shifting the mass to the right hand side, and we have this calculated. Okay, this is the process of convolution in two-dimension values. All right, before we begin, can anyone extrapolate from what I explained and explain to me how else convolution would work? Try to imagine. What I show you is the way that you can do convolution in one dimension and two dimension, but there are also plenty other ways to do convolution. Right? Can you explain that to me? How can we do that? Right? You can do it by using annotation tools here in Zoom to explain that to me. I will allow the sharing first. Security. Enable share screen. Yeah, you can share the screen. Or you can just write the idea onto the current page. Right? Can you try to explain to me what else can you do with convolution neural network? Right? What I can I be different from one dimension, two dimension? Can it be more? What type of k that can be represented? Right now you can see that k has to be a mass or just a vector that run around in the dimension that's specified. Can it be also variants? Right? Any idea? I'm waiting. Think about a variant of CNN. What else can it be? What else can it be? There are many other else, other variants that can be done. What else? Right. For example, from one-dimensional data, like a speech. No, speech is too much. From one-dimensional data, like a word. I like noodle. Very much. Right, something like that. And yeah, we see that it's like very much. Okay. From a vector of word in text processing, you can extend this vector of word to the latent dimension called embedding dimension, which we'll talk about that in representation. This is the latent dimension. So you can do two-dimensional convolution in one-dimensional way as well. Like instead, this is the data, right? The eye. Right? We have eye like this one. You can have a mass that instead of having a small mass 3 by 3 run around, you can have a mass like this. 3 by k. Right? It can be 3 by k. Right? That would move to the right to generate a feature map that also in one dimension. This is a variant that is possible. So it means that if you have a sequence of data, and then you can represent those sequence of data as higher dimension, you can still use a low dimension convolution to process that sequence of data in order to detect the pattern. In that sense, you have a lot of feature map. Each feature map would correspond to one mask, say mask K1. This is the result of mask K2. This is the result of mask K3. So this is also a variant of the convolutional neural network that can be done. This is used in if you use convolution with the text data. And this is a way that can be done. Or you can do the convolution with the mask in 3 dimensions. Right? Now we have 2-dimensional mask, 3 by 3. Let's say if you have a data in times, right? You have spatial and temporal all together, and then you want to create a model that take multiple frames of data and process at the same time. In that sense, you can use the 3-dimensional mask on the 3-dimensional data. Now you can further imagine in that regard to use like a 2-dimensional mask and 3-dimensional data. Well, that can be done. You can use the 3-dimensional mask that move, right? That move and convolute in 2-dimensional way. That can be done as well. So there are a lot of variants that can be done here. What I would like to tell you here is that the CNN doesn't limit you to work just image data. It can work with authors type data as well, given that the thing that you want to learn is a type of kernel that transform data to another domain, right? So that's the core of CNN. Now let's take a look at and what are the advantages of CNN. Right? When you learn the math, when you learn the convolution, what good is it comparing to, let's say, fully connected, right, that we learned it back in 3 lectures ago, last month I think. Right? What are the advantages of the convolutional network comparing to that one? Right? There are the 3 obvious reasons to use convolutional neural networks. The first one is the sparse interaction. Right? Second, the parameter sharing, and the third one is the equivariant representations. What are they? What are these benefits? Let's take a look. First benefit of convolutional neural network is in terms of the sparse interaction. What does that mean? Right. Let's take a look at the picture below first. This is the network when you use the dense network to process the data. Each input is fetched through all the processing node, right? That means one input is processed by all the node. But well, just think about this. If you have a picture of bird, that can be just like if you take a look at my my screen now, right? If you take a look at my video right now, you can see that this is my face, right? The area of my face, not the author, right? Not the entire area here. Right? That means the image, the interesting part might be if you take a look at my face and want to identify that this is me by looking at the face here, right? Just in this region. That means only some portion of the image are interesting. Right? Some portions are interesting, and you want the model to be able to narrow down and detect those areas. Okay, sparse interaction means that convolutional neural network will allow you to identify the sparse location that are interesting. Right? It will interact with the sparse data. Like part of the data are interesting, the other parts are not. Right? When you use it with this one, it can highlight which part are interesting by using the mask, because the mask would move around. Right? Once it moves around the location, like move around my face here, then the model can detect that these are the regions that are important in order to perform face identification. Okay, so this is a sparse interaction because we have a mask to move around, and then it means that for each of the result of feature map, only the nearby regions of the location would be corresponding to something that happened at that location. Okay, So this is cool. You can have a way to narrow down the location of the thing that you want to learn. If you take a look at the other way around, right? Let's take a look at like from the top. For each of the output feature map here, each of the output would come from just only a portion of input. It means that for each of the output, it acts as a detector of a certain location. Unlike the fully connected version. In a fully connected version, it doesn't care about the spatial location, right? But you can see that the spatial location is preserved in the convolutional network, which is nice. Right? You have a way that would allow you to localize and preserve the detection of patterns in the certain locations. Right? So this is why sparse interactions are important. Sparse interaction also does not limit you to process the data if say the patterns had to come from overall, let's say not only my face that you want to classify, but also what happened, where am I here, then you need to take into account of the whole picture here, and that means not just the way I sit here, but also that like we have cabinets here, we have like windows down back there. You can classify this as office. Now you need to take into account of the whole pictures. In order to do so, that it means that the detector might have to detect something that is much more than just one location. How would that be accomplished here? It can be accomplished by having a deeper architecture. When you have a deeper architecture of CNN, the one that is in the deeper region would represent the abstract representation of those that are in the earlier regions. So it means that the details will be captured. What should I say? Well, the abstract version will be captured at the latter stage of the network. Abstract version, like what? Like if you perform face detection, the abstract version can be the shape of the face. It can be the hairstyle. It can be the location of mouth and others. Those are the abstract representation. The detailed representation would be something like the shape of the eyes. Maybe your face has certain texture. That's the details, right? So each of the layer would represent different things. By having it having them stacked into multiple layers, it allows you to represent the whole thing, represent the whole image through this deep convolutional way. Okay, sparse interaction. What does it mean? Right? Each hidden unit is connected to just a patch, just a the local area. That means if you have like this receptive field or the mass on this area, that it would detect only inside of this picture. And you can see that the one here and the one down here might not be interesting. You might want to use just the middle to perform classification of the, for example, of the flowers here, right? So each of the mass would result in one feature map. So what does that mean? It means that let's say starting from an image like this one, you may have first a mass, the first mass. Learn that the first mass produce the feature map. So say this is I1, K1 produce S1. Now you may have this I2. Oh no, sorry, that's only one I. Only one I. So oops, sorry. Draw it again. Just one I. And you have one K1 give you S1. Now using the same I, you can have K2, learn that K2, and then K2 give you S2, and K3 give you S3, and so on, right? The more you have the number of filters, the deeper the feature map would be. Let's put it in this way. So when you have multiple filters, usually in the representation of the CNN of the convolutional neural net, it would be represented as the depth of the filter. But I want you to clarify here that it is not exactly the depth. It is actually multiple filters that are convoluted, and then you have like multiple layer of feature maps that can be used as the materials on the next stage. Okay, the depth here, the number of filters, is hyperparameters that need to be tuned for the CNN, just like the number of nodes in each layers that we learned that in the deep forward network. This is sparse interaction. Okay. Next is also another important features of the convolutional neural network. This is called the parameter sharing. Many times you will see through the study of deep learning, if you are into this field, that the more you regularize the network, the better the results would be. What does that mean? It means that if you have like a dedicated link from input to output, and then you need to learn the weight of just this one link, this is not a good idea for this network at all, because it means that you are trying to specifically link input to processing without generalization. The idea of learning is to generalize from patterns. Generalization is a process that does not limit to just the neural network, but also to biological organisms. That when you learn something, you don't want to learn just one piece of information. You want to learn from multiple pieces of information and then generalize them both in positive way and in negative way, and then generalize them into knowledge, and then generalize them into the insight of your model. The model can be overfitted if you take input just from one node here. That means convolutional neural network is good in this way because the weight is shared, used on each of the feature map. Right? On each of the feature map that is generated, it uses the same weight that need to be learned. That would generalize the way that it learns, because it is regularized so that it means that one feature map, it is limited to the processing of just 9x9 grid here. By learning this 9x9 grid, it allows you to learn one way to detect certain patterns. And by having multiple filters, you can let the system determine how many filters that are required here. Right, this is the concept of parameter sharing, and it is very important core concept to deep learning, to the learning of the task. You will see later on, right, not just in this one, but also in the other context, that if you want neural network to perform very good, you need to regularize it a lot. You need to have a shared task, like one task performing one thing, another task performing another thing that are similar to one another, and let the network learn from a bunch of examples, right? So that it can generalize pattern detection way. Okay, so this is parameter sharing in CNN, right? Because well, you can see that S2 is calculated from X1, X2, and X3, right? And this is the middle weight. This middle weight is again used to calculate S3 and take X2, X3, and X4, but the same weight. So again for the X4, using the middle weight, the same middle weight. And when it is learned that the update of the weight will be done once you have certain prediction, and then backpropagation would update the weight, and this weight will be updated according to the whole thing here. All right. So it is quite nice in terms of the properties that it would generalize and then regularize at the same time for this convolutional neural network. Right, so how does it work in terms of sparse interaction and parameter sharing in neural net in the learning of this? When you have something like image here and you have a mask, suppose that a mask is learned so that it would detect the edge, it would go in this direction, going up and going down, or left to right, top to bottom, through the whole image, and then the feature map would look like the right hand side, right? The detection of certain things out. Right? The left hand side is the original image, right hand side is the detected version of the image. But it can be different. It can be blur version, it can be detecting just black area, it can be different things, right? Depending on the types of mask that we have here. Alright, parameter sharing would allow you to learn parameter across the unit. Okay, across the unit. So one parameter is used to generate a certain type of feature maps. Another is used to generate, the second one is used to generate the next feature map, the third one to another feature map. So it means that different feature map would be used to detect different patterns by means of parameter sharing. Right. The last one, which is also an important one as well, this is called the equivariant. Okay. Equivariant means that it's like if you learn signal system, this is the time, what is the LTI, time invariant, right? This is equivariant. Equivariant is results from linear operation. That means if you have input and then shift the input before processing, when you do it like this, you have the shifted output, you get the same thing as having input and then process and then shift the output, and then you get the result and shift the output. Convolutional neural network gives you the same output of both process. Well, what does that really mean? It means that if you process, if you let the system, by convolutional process, either you shift the result first or shift the result later, doesn't matter. That means you can have the shifted version of input and then pair it with the shifted version of output. You can have the system learn the way to detect the location. How come it works? Because let's just think about it. If you shift the location like of my face around, like I am here and I am over here on the image, the mask has to go through the image anyway, go through the whole image, and it would detect my location. So this is a bit of equivalent that I shift it so the image is shifted, but in any case you can still detect the shifted version of the output. Right. So these are the three important concepts of convolutional neural network. I would say three benefits of them. Now let's take a look at different way to implement the network. Right. Convolutional neural network alone would generate a set of feature map. Usually it would be written like this one. You have image, and then in this image you have the convolutional map, and this convolutional map will be used to generate the feature map. Right? And you have a multiple of feature map because you have a bunch of, let's say, k. This is k, a bunch of feature map. So you have like 3 filters, you have 3 feature maps, but you end up with the data that is much more than you start with the initial process. This is not a good idea. Even though you detect different patterns, you want a way to summarize the pattern down. This summarization is called pooling. Okay, how does it work? Let's take a look. Usually in convolutional neural network, the process would be can be divided into 3 stages. The first stage is the convolution. You can perform the convolution to produce the result that will be fetched into activation. Okay, so start with convolution, then passing to detector stage, which need to be passed through something like the ReLU, the rectified linear unit, or sigmoid. Right, through the detection, usually ReLU detection stage. And then the third stage is that once you have a lot of channel, you might want to reduce the data rate so that the data will be represented in the lower resolution. Lower resolution means more abstract. Right? It's like viewing things as blur. You have more abstract version of that. We kind of disregard the detail to get just the main pattern. Okay, so the third step is to accomplish that by using pooling function. Right, the pooling function, the pooling stage here would pool the results together, summarize them to be lower resolution, so that you have the results for the next stage. This is one convolutional unit implemented in Keras and other software. Right. How does it work in terms of pooling? Let's take a look at it in one dimension first. So the values in the bottom rows, right, are the values that are from the detector stage, and the values in the top row are the values from the pooling stage. This is a process called max pooling. Okay, max pooling would pool the max value. In short, it actually compares the values, right? 3 values here. Compare this. For this one, it will compare 3 values here and detect the max. And you can see that here's the max. That's why you get the result as the max one. This is max pooling, right? Pooling the max value up. Right. Okay. So it's sensitive only to the maximum value in the neighborhood, not the exact value. This allows you to smooth things, to smooth the detection on the region, so that the nearby firing up of the detection can be pulled into the summarization. You can also further reduce the dimension of data. For image like this one, this is 4x4, right, grid. You can do the max pooling with the factor of 2, downsample by 2, so that it would downsample this one to so the green here. If you use max, this is max pooling, then you get the 21 here, 21. For the orange square, you get 12. For the red square, you get 18. Blue, you get 10. This is max pooling. Average pooling works the same way, but instead of drawing the max, you try and calculate the average of that. Right? Which one is better? Well, I have often been asked which one is better than which. My answer for these techniques are the same. Depends on the situation. In some situation, max pooling is good, especially in the data reduction way. But in some situation, you don't want to do that because max pooling lose certain resolution of the gradient of detection. You might want to do average pooling. For example, you would perform something like feature extraction doing the Siamese neural network. You might want to use average pooling instead of max pooling because it would kind of average things in the same region down. Right? But well, these are detailed configuration of the architecture that you might want to consider later on when you have a certain design requirement that need to be accomplished, right? But in any case, this is the pooling process. Pooling process is a process that is usually come after the convolutional stage. Pooling also enable the network to learn multiple versions of the same thing. This is cool in a way that if you have multiple network that results in different detector, like this one detect 5 in a rotated manner, this one is a normal manner, and this one is a quite slight rotated manner. Using max pooling would allow you to detect multiple versions of the same thing. Like if the input coming up and then it detect the rotated manners of the image, it can detect one of the node that is represented as the rotated version. So max pooling and the pooling technique would allow you to learn the modification of input. Right? You can fetch into the system the modified version of input and let the system learn the variation of the input that can occur. Okay, that means, well, you might have a way to generate your data now. Right? If you have image data, you can rotate the data, scale the data, doing the F5 transform, modify the data, and then fetch that into the system so that the system can learn the patterns. and then pooling would do the job in terms of isolating the pattern that is detected. Pooling also should be combined together with downsampling, right? Why doing downsampling? Downsampling is a way that you try to reduce the data rate, like in this picture. From 6 points, this is reduced to 3 points. So the data rate reduced by 2, so that you have the upper value here are more abstract than the lower one, because you kind of detect just what happened in that region. Okay, this is done by specifying the striding. Right? The striding can be specified in Keras, in the striding parameters. Striding means that if you want, whether you want to do just convolution and then stride them, that is not doing the full convolution, but you're kind of taking the step of 2, that is jump to the next one, then perform convolution, perform multiplication, then jump with the step of 2. This is called striding. That means you try kind of reduce the data rate, like you perform convolution and then do downsampling of the data rate. So the same thing. That means you can specify the striding, the stride parameters in the convolutional process, so that it would reduce the data rate down. Okay, this is the stride of 1, and that means the mass here, the mass would move 1 step at a time. This is moving 2 steps at a time. Okay, the stride equal 2. All right, so that is the striding, right? The convolutional neural net also allow you to specify the grid different way, like the left hand side here. This is the fixed size network. Fixed size network means that here you have input of 256 times 256 pass through convolution, then pooling to 64 times 64 with the depth of 64, right? And then pass through convolution again, and then you do the pooling to 16 times 16 times 64, which is the number of filter. Okay, then using reshaping, flatten them, then you get something like 16,000 units fetched to dense, and then results softmax. This is like fixed size. That means the whole thing here can work only with fixed size input, but you can also specify it like this one, that is starting from 56 times 256, do the convolution to 64, output at 64. At this stage, instead of reducing by doing the striding, you can just specifying that the output pooling function should be 3 by 3 kit. Fix the size, right? Because the size here is fixed. It means that no matter what size of the output of the input that you want to feed to this, it will be pulled down to just 3 by 3. This allows you to implement the variable size, right, on this part. Allow you to have multiple versions, multiple sizes that it feed, and then at least it will be pulled together to the same resolution here. Okay, and for the right hand side, it's quite nice one. This one is actually you can see that this one doesn't have dense layer. Usually at the end, after reshaping, you need to have the reshaping vector and then pass through dense layer. For this one, it passed through convolution, pooling, and convolution, and then pull into just one value as by 10,000 as the output. You can do it this way as well. You don't need to have softmax as the output all the time. You can also implement it convolution alone, and then use the convolution to do backpropagation to learn the weight. Okay. Actually, some of the successful models use this convolution only way, but I would say that majorities of the techniques like the image classification, like VGG and the others, they use more of the left-hand version. They have a kind of fully connected at the end to do classification. or if you have the data in sequential manner, you can have something like CRF, HMM attached to the end, right, to perform classification. All right, so this is variable size. This is like a trivial issue in convolutional neural network, but well, you need to specify them in the model. It's called zero padding. What does it mean by zero padding? If you does not specify padding, it means that you lose the dimension, right? Because say if you do it 6 by 6 grid, and then moving that along this data here, you can see that for the point here, it takes the values from this 6 point, but the value on the left hand side here doesn't exist because it doesn't have enough data to perform calculation, and that would reduce the data rate down. So the dimension would be lost through the process of convolution, and this sometimes is not desirable. Right, you want the data on each of the convolution process to stay the same, and that is called padding. That will save you. Right, padding is done by add 0 to the left and the right hand side of this, or if in terms of the image, add 0 to the borders, and then you let the system convolute for the border points to take in those 0 value at the border. It doesn't matter because the math has to go through everything anyway. So by doing padding, your data will stay as stay the same throughout the convolution process, right? So this is zero padding. Okay, so the process of in convolutional neural network is simply a process of convolution to detect feature and pooling to reduce the data rate. Okay, so from the input image, right, when you use one mask, you get one feature map out, and you have like multiple versions of the feature maps. Actually, the input image, if you have like color image, then you actually have three, the three red, green, and blue channel. And the convolution to generate feature map will run through every one of those, right, to calculate the feature maps. One feature map out, and then you would have multiple of them. Say that you have 4 feature map corresponding to 4 masks, and this 4 feature map is subsample or pool to have lower dimension, and each of these, and you can see that here, each of these is convoluted to produce one point here, right? One point here in the feature map. You have a smaller size and 6 of them, and then another one, and then finally fully connected, right? From this, you can see that the dimension of data is reduced through the process of pooling, and the features is also becoming more abstract. How so? At the beginning, when you downsampling the feature that is detected, you get the smaller version. Smaller means if you represent the smaller version with the same dimension, it would represent the coarse. Coarse means the rough version of the pattern that you want to detect, right? So this is a way of pooling and subsampling, and it has been implemented in many of the examples here. Like in this example, to do image classification, you can have a sequence of convolutional network, and then the detector, ReLU, and then convolutional network again, and then ReLU, and then you can pool to summarize, reduce the size, and then do convolutional network, ReLU, convolutional, ReLU, and then pool, and at the end doing the FC, the fully connected, to classify which of the class this should belong to, right? So if you take a look at the architecture of the CNN in different tasks, it looks the same. It will look like this one, except if you have like a spatial architecture that we'll take a look at. I think the lecture beyond recurrent neural network, we'll talk about the spatial type of architecture like Siamese neural networks, attention, and how to implement them. I will show you basic implementation there. Okay. Right, this is CNN. Just And each of the layer, the picture here show you that the result of convolution, each of these are the results of the feature map, example of them, and passing through ReLU, it would kind of squash the convolutional values into just the range of 0 and 1 or the ReLU values. And then again convolution on this the ReLU and getting a bunch of them, and then again, and you can see that the resulting feature map here would represent different patterns to be detected to tell that this is a car. Right, let me take a break for say 10 minutes. After the break, we will take a look at the ImageNet challenge and also the implementation of CNN that I gave you in the notebook. You can download the notebook and then open, and then I will explain it all through that. Right. So for now, let's take a break for 10 minutes. I'll be back. If you have questions about all right, let's continue. Right, so let's continue to another a set of examples on the proper architecture for convolutional neural network. We will take a look at examples from the ImageNet challenge. ImageNet challenge is a competition that compete on a way to perform image classification. Okay, there are millions of images to classify into thousands of categories. The goal is to classify images into correct class. Okay, so there are multiple of accomplishment. In 2012, AlexNet proposed the use of a series of convolution process and striding in order to summarize the data down, and then used a fully connected version at the end to perform classification of image. This is called supervision, the model. And AlexNet actually used a series from the image. It has like 5 convolutional layers and fully connected layers. And in the paper here, it demonstrates that it can detect patterns at different layers through the process of train using the stochastic gradient descent that you implemented in your first lecture and your earlier lectures. And from this, there are a number of neurons and parameters to optimize, like 60 million parameters to optimize that. The final features are 4096 dimensions for performing classification. These are examples of the feature map related to convolutional layers, of the first convolutional layer, some of which would detect the specific pattern, some of which would detect the balance in color. Okay, so in 2012, AlexNet performed better than the rest. It marks like the start of the deep learning era, like around that time that it can perform classification of image, right? So supervision gives you like the best result. And through the years, 2016 and 17, here we have like, and after 2015, the system has now surpassed human in image identification. Let's take a look at the VGG and the ResNet that are the results of this competition. This is the design of the VGG net. VGG net includes 60 layers of convolution and not including pooling. And VGG net strictly specify that the mask has to be 3 by 3. So it uses just 3 by 3 and then convolute in the deeper layer, right? So that there are like 138 million parameters to optimize. you can actually download the pre-trained model, and I actually have certain demonstration to download the VGG model to perform classification in the notebook. So you can use the pre-trained model to perform image classification, right? And in 2015, the ResNet model, ResNet is proposed by Google to incorporate the residuals, add the residual layer. This is the residual link. The residual link would jump past the layer, the convolutional layer. Like you have 3x3 convolution 2 times, then you have the skip here, and the results would be the addition between the image here and the convoluted results, right? So you have a skip one after another. The reason for this skip is to allow the gradient that occur at the end to propagate back directly, to the earlier network, easier than passing through a bunch of convolutional layer. This is the deeper 34 layer convolution CNN. VGG use about how many? I don't remember. 16 layers convolution. And ResNet use 34 layers convolution with skipping. Right? This skipping would allow you to have like the deeper model, and can still update the weight at the earlier layers. Okay, so this is nice. Allow you to update things in the earlier layers. This is like state of the art that you can also download and use in your model right now. Or even if you want your model to perform different tasks, you can start with ResNet or VGG, and then you can cut the classification part at the end out and let the model learn different things. Like if you want to perform, say, brand detection, right? Brand detection to detect which brand this should be used. You can use ResNet or VGG and then cut out the classification, the fully connected part. The earlier part would represent the way to do classification anyway, no matter what types of image that is. Then you can attach this to another network or train it with the new data so that the weight will be adapted toward the task that you want. So that is the way that you can modify using coding to modify the deep learning, that by like cutting output and then use part of the network to do different tasks. Right? Okay, so this is residual net. By attaching the network like CNN with RNN, with the recurrent neural network that can generate, doing the language modeling, generate the language. You can match the data between input, image, and the output, the text, to do the sequence generation from image. This is called image captioning. In order to do this, you need to have a large set of data. This is one of the limitations of the deep learning. You need to have a large set of data. If the data is not varied enough, your model will be overfitted and it wouldn't work in other cases. If you have large enough data, you can train it, and then the model would can do something, produce something cool, like once it see the image here, you can express that this is the girl in pink jumping in the air. This is the black and white dog jumping over the bar. It can do something like this one. But it can also do something that is seriously wrong, like explaining something that is out of the context. These are just good examples. But in any case, you can see that this is quite promising, that it can explain what this picture is. Actually, it's not explaining per se. Understanding neural network, it will allow you to know that it's not like the network know that this is a girl. No, it is not the case. It is actually associated these patterns of data with a girl in pink jumping in the air. Right? But you need to have a lot of girl picture and this different dress in order to make it able to describe it this way. right? CNN can be also used to detect person doing the screen passing, which part of the screen is the location that you want to know, and there is already a model that do this called the YOLO that can detect object, location of object in the scene that is implemented. But if you want to present that in your research paper, feel free to do so, right? Explaining the architecture and how it works, right? On this end, I would like to emphasize is that at the end of this semester, we will have the research presentation that each of you has to pick one paper in deep learning, and then present that paper, particularly in terms of the network architecture that paper used, explain the mathematical idea of that paper on why you want to do that. You have 1 week to confirm to me on what paper that you want to read and present. Say, I will put the Google Sheet so that you can put your papers and the reference onto that Google link, so that I will take a look at the paper to see whether that's okay or not. All right, so we have about 80 of you guys, so it should take, if how many days would we need? Suppose you have half an hour per person. Half an hour per person a day, you would get to like 6 topics. I need 3 days. Right. So yeah, we get a presentation on the last 3 days of our class. Right. After we are done with the spatial architecture in the deep learning, right. And so you probably need to find out what type of paper you want and select it within this week, and put that link into the link that I will provide and study them. Right? That is one of the deliverable of this class. That is, you have to study at least one research paper. Think about it as doing literature review. Right? This is like pre-literature review, just one paper. Okay, although it's on the deep learning topics. All right, so this is all for the lectures. Next, you take a look at the coding. So before we go on, do you have questions about the term project, or not the term project, term paper? I can show you the description in the syllabus. Right here, right? The research presentation consists of 20%. So you just need to present the topics in actually just the architecture of the model in the paper. The presentation should last about 15 minutes. Then there's a question answer for 5 minutes. Yes, that's about that. All right. And today we will have, all right, we have a question here. Actually, we can turn on the mic and ask. It means we choose from a listed topic from me? No, actually, you should search the research database. You can use Science Direct, Archive, Arxiv, or the Google Scholar. Search a paper on deep learning. Search a paper on deep learning. It can be about architecture, optimization, whatever, right? What I want you to present is the core concept of that paper. Right? What is the mathematical foundation, the method presented in that paper? So I don't have a list for you. You need to find out what types of network you want to present. There are bunch of them. Like I think there are a lot of work that are worth presenting, like GAN, the generative adversarial network, or encoder-decoder architecture, equation answering architecture. What else? The attention, I will talk about that, transformer. Yeah, lots of them, right? Sequence-to-sequence model, 3D convolution, video processing. Yeah, there are like a lot of things that I cannot cover in this course alone, right? Because we have covered just the basic neural net and then mathematical underlying. But there are a lot of application and a lot of variations on the work. So I want you just to pick one and present the core concept, the architecture, explain it in terms of mathematical detail. I will post the project description onto the group within this week, this few days. Similar to the assignment number 3, right? I will post that tonight actually. I will post that tonight after the class. The assignment number 3 is still image classification. You will see that later on. All right. Okay. If nothing else, I'm going to move on to the coding. We still have the coding to cover. Okay, let's take a look at the code here. What I'm going to show you here is building the image classification using the CIFAR10 data, right? The CIFAR10 data is computer vision data, consists of 60,000 32 by 32 color images, and these are the images from 10 classes: airplane, automobile, bird, cat, deer, dog, frog, horse, sheep, truck, right? And these are quite famous, and you can use it as a benchmark to do a lot of job here. We will build a classification model that take in this image and then classify the image out as a class, right? Okay. Start with, I'm going to load the data here. This is the Keras dataset contain a built-in dataset that you can use to test the concept, you can use to learn. So there are a lot of them. I will use CIFAR10 here. Actually, we did use some of them at the author lectures. CIFAR10, and then load data will give you the train X and test X, and then we need to, and then this bunch of code would plot, show the image to you guys. Okay, these are the images. You can see these are quite low resolution, 32 by 32, but you can still guess what images they are. Then let's prepare the data. I have train Y here. These are the train Y. Train Y are still in numeric format. I'm going to convert it to the one hot format using two categorical, and then you get this one hot format, two categorical. For Y test as well, two categorical, and you get this Y test and Y train. And for X, it needs to be scaled to 0 and 1. Why doing that? So that the gradient would be represented as in the similar manner. Right? Rather than having one weight dominated the other, you better scale them to get the same range and then fetch everything into the network so that the network will detect mainly on the pattern. This does not require for all the cases, though. I would say that for images, doing this is fine because you know the image range from 0 to 55. But if you work with different types of image that contains finer resolution, you work with different types of data, you don't have to do it this way. You can modify your method to fit the criteria. Okay, this is to extract the number of class. There are 10 classes here. And next is building the model, right? Just like in just building the dense layer alone, I use sequential implementation. This is quite easy. More advanced way is to build it using the model API. I have not shown you that because we are not going to focus on the coding here. The convolution, 2D, max pooling, and dropout, and these are the convolution, and max pooling. By specifying pool size to 2 by 2, then it would kind of reduce the data rate by 2 by 2. So convolution, pooling, again convolution, pooling. Right. And the number here is the number of filter that you want to learn at each stage. So there are 32, 64 here, and then this is also 64, 64, 128, 128, and passing through dense layer at the end. And by specifying padding to be same, it means that you want to pad the data so that the dimension will be the same for all of for the input and the output. And the last one is the dense class with activation as softmax in order to perform classification. Right. So let's load the model in. And these are the summarization. You can see that the number of parameters has actually become large at the dense layer at the end. Right. So at the beginning it has lower number of parameters, but at the end it's quite large here, right? Because it's like a lot of parameters to learn. Okay, this is max pooling. And then compile the model. Here I use SGD. Instead of specifying just the name of the model, I initialize it as an object, as a function here, so that I can specify the detail like running rate, momentum. Remember last time you can specify the momentum to get using the momentum to do the smoothing of the learning rate, and the decay, Nesterov, which you want to use the Nesterov criteria. And compile, this is categorical cross entropy because this is multi-class case using SGD as optimizer, and evaluate using the accuracy as matrix. And then fit the data with batch size of 32. Then wait. Each of the step here is one batch of calculation. It will take quite a while. I'm running on a notebook. If I use the GPU computer, it will be faster. So each of the batch, once finished, it would update the model parameters. That's why you see that the model improve at each iteration. Okay, while we are waiting, let's talk about the project. Okay, I will show you at least the project description that I got last year. So I haven't prepared for you guys this year. The term paper explanation. No, it's nothing like that. So basically you just need to select one paper and then present the work inside the paper. For example, let me give you an example of last year paper. Last year, one of your senior, this one is not okay, it's too complicated. Select this colorful image colorization and then explain how colorization is done. This is colorization. You have the grayscale image and then you train the model to colorize the image. And what I'm interested in is not the task itself, but here what I'm interested in is in terms of the architecture. So I want you to explain the architecture. Why does it work? Right? That means you probably need to explain the loss function used on this work. You will need to explain how come it can map from the grayscale into color. Right? So this is what you need to do. Right? Or let's say about this one. This is to use it to scan for X-ray, and this is the architecture using convolution, a simple convolution actually, to do image classification here. So this one is quite repetitive in the sense that, well, the data is nice, but for this course, I want you to find an architecture that I have not covered. This one is already covered. So in terms of the originality, in terms of the novelty in the architecture to present, it get the lower score than the earlier one. Okay. But in terms of the explanation that the person who select this paper explained to me, it's quite clear. Although I have the score in terms of section. So let's put it this way: I'm going to upload the evaluation metrics as well as the topics. As at the explanation of the paper that you should select and the process that you need to do, like presenting 15 minutes and question and answer onto the group. I will put the description onto the group there so that you can work on and then maybe select a paper and then tell me which one you select. Right? It will take quite some time. I actually have the model that is already finished loading, but not sure if I put it here. Score model _1. Let me check. Do I have it online so that we don't have to wait until it finish optimizing? No, I don't have it online here. Well, let's wait then. So here is the end of the first epoch. Right, one epoch equals like one iteration through the whole data set. You can observe that this is the training loss and the training accuracy. It increased. And then it comes the second epoch. Go through the whole batch of data. From the first epoch, we got the validation. Using the validation test, set, X test, and Y test, we get about 0.39 validation accuracy. Then let's wait. It takes about 5 minutes to complete one iteration, so that we need to wait for another 15 minutes until this is finished. Any question about the project, the term papers, the research presentations? In the meantime, let me work on the assignment specification. So, yes?
I would like to know the rubric, if you could get the rubric for how we're going to be assessed.
Sure. Yeah, I will post the project description all together with the evaluation metrics, right? Evaluation rubric on how you would be on how you would be scored in that.
Okay.
Sure.
Thank you so much.
For the A3. Well, while we are waiting, let me work on. I'm going to work on the assignment description and then upload to the group. We will still have to wait for another 10 minutes. There's a question coming up. Can we apply CNN on text data? If yes, how do we know when text data is redundant? This is interesting, right? You can do that using the text data and then perform CNN. But rather than doing the CNN just like what we saw, there is a certain modification that you need to do in order to perform that. I will show you one variant of text classification using CNN in a moment. All right, let me finish this description first. All right, let print it. I should use this one rather than that. Got this. I'm going to upload the file, and this is A3. Assignment 3. Convolution. Let's call it design of convolution. Convolutional neural network. Okay, the due date is it should be the 2nd, not the 3rd, right? Almost. Let me drop it and fix it here. The 2nd of November. Got 2 weeks to do this. Now, actually, with this waiting, I don't know what to do with editing the video. This is the description. Build your own convolutional neural networks. Come up with your own architecture and classify the data called fashion MNIST. Fashion MNIST is a grayscale data of the fashion item to classify into 10 classes. You can take a look at this link. You can load it from Keras API, and here are the things that you need to do. Right? Load and explore fashion MNIST data, design convolutional neural network, justify your design, why you design that way, train your model, evaluate the result. The thing that you need to submit to I should put it there, right? You need to, I already put that. You need to submit your report as a PDF to LEB2. The report can be the PDF version of the notebook that you use. Right? Just print it as PDF and then submit to LEB2. Okay, and I'm still I still owe you the grading of the earlier assignment. I will do so in soon. Should give you also evaluation metrics on those one as well, right? Okay, so maybe next week I will give you that grading. Okay. All right. For this one, I need to upload it to the group A3. All right. Okay, we are here. Now let me explain how to use CNN with text data. Usually when you have text data, you would have a sequence of text. In text classification, one of the first steps is to encode the text into the embedding. Encode it into, let me find a clear space to use. Maybe I should share this as a whiteboard. Okay. To work with the text data using CNN, you can say, let's say, I like this movie very much. We need to encode the text into not one hot encoding, but represent it as a vector of representation. Using this is called the embedding. Right? Or think about it as the latent variable. This is a better representation, for text. The reasons why, because it's kind of encode the context of the text into this. How do you come with this? You need to train it in order to let it learn what encoding should be the best. Right, usually this will be in the text mining concepts, okay? So let's say you can encode each of the words using a set of value. Right, for this one you have a number of them here. Let's say the dimension here is 300. Alright, means that you have a multiple channel of the sequential data. And what to do then? In order to use CNN with this text data, well, if you just use the square CNN, that would mean that you are trying to go through the time dimension, the sequence dimension. At the same time, you want this to capture the embedding dimension, which doesn't make sense actually, because the data actually has just the temporal or the sequence dimension. So the researcher has come up with the idea that, okay, you can do the CNN with this by capturing deciding your math to be like this one. So, let me draw it here first again. Come on. And the math will look like this. So instead of having something like 3 by 3 math, you now have 300 by 3, right? 300 by 3 math. And this 300 by 3 math would be compute and generate the feature map. Let's say you have 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. So this square here would generate the data in this point. And then the model would try to learn these parameters, a number of them. So we have like a number version of this one. Right? This is a way that you can use convolutional neural network with one-dimensional data, okay, by expand the dimension into more than one dimension and then run the convolutional neural network throughout those multi-dimension. Right? So it is all right. This is one of the combination that can be done, and it has been used with the text classification. So this is convolutional. How about pooling? Pooling can be done here to reduce the dimension. So let's say you have the sequence with the length of 1, 2, 3, 4, 5, 6. You can reduce it to just say 3 by doing the max pooling. Yeah, and then you get the pattern detected. Then you can perform convolution again, and so on, right? After this, you can then fetch this to the fully connected to do the classification. Right. So redundancy in text is done by representing it as context like this one. When you represent things as a context like this one, if there are certain redundancy, then it would be detected. It would be like projected in terms of the latent context anyway, right? So which word is important, which is not in terms of context, those will be learned through the process of learning embedding. It's one of the text representation concepts. If you are interested in this, I would welcome you to taking in the next course in either text mining, or maybe you can just select a paper in text representation, right? Textual representation, which use the sequential model, and then you can explain that to the class about embedding, about autoencoder, right? And that can be part of your research paper as well, right? Now let's go back to the slide and to this. All right, we are already at the fourth epoch. We got the results just about 50%, right? Actually, the model here that I have is trained for like 10 epoch. Model is still good. You can determine whether the model is overfitted or not by take a look at comparing validation accuracy and the improvement in validation accuracy. This is still better, right? And the loss still reduced in terms of validation loss comparing to the training. If they are still increased, then it means that the models can still go on. And you can run at a bunch of iterations to determine how many epochs that are required, and then once you determine that, you can then rerun it again to get the better value. There is actually a better way to do something like early stopping, but well, it's like a trick that you determine whether the error kind of drop, and then you can just stop. But it doesn't guarantee to be good all the time though, because sometimes the model accuracy and the loss can be quite fluctuated, especially if you train the model with something like one-shot learning that we will take a look at in the spatial architecture later on in this class. Right, so we will work well with the one that we have at the fourth iteration, but I would recommend you to further train this model to say 10 iterations, see the results, whether they are still can be improved, and then evaluate the result. For now, I'll just show you the code that allows you to do so. Again, if you have just like if you have the GPU and run this on GPU, it will be faster. Good GPU, right? It will be faster. But I run it on Mac. Mac the version that I have use ATI, I think, Radeon, right? Not the NVIDIA, which is a pity. And it doesn't have the GPU core anyway. It doesn't have the CUDA core, so that means you cannot parallelize the process in computing. You can actually, but it's different framework, and TensorFlow relies on CUDA framework to do the job. Almost there. All right, it is finished. We got about just 54.7. Well, you can try running for more, but I have limited time. So here you can use model.evaluate to evaluate the X-train and X-test. Let's put verbose to 2 so that we can see the log. It's probably need to do it in the training. So here, it's done. Verbose 2 is kind of ignoring all the results. we get about 54.78, the same as the above because I used the test set to do validation. Right. Now let's take a look at the preloaded model. This is the pre-fit VGG model. VGG model looks like this. It's take in the 224 by 224 by 3 image, and then fetch to a series of convolutional and Lelu. This is the by 64, two of them, and then max pooling, and then by 128, two of them, and then pooling by 245, three of them, and then pooling again, and by 512, pooling to 14, and to 512, and then pooling to 7 times 7, and then pooling again to using with fully connected, and at the end with softmax layer. Right? You can load the pre-fit VGG using the Keras application VGG, and then import VGG 16, then you get the pre-trained model. That easy. Right? This pre-trained model need to take in the image of the size 224 times 224 times 3. Okay, the color image. Now this is my bird from elsewhere. I take the one of the picture, not my own picture though. I got this one. This is a picture of the bird. I suppose it's not in the data set, right? You can just download it down, and then we will use this to fetch into the network to see what patterns that the network detect at each layer. We will start with visualizing the filter by doing the for loop through the network. Right? This is for model.layers, and then we get each layer out. So think about it as a bunch of layers. We kind of go through all the layers using model.layers. And if it starts with conv, we kind of having the word conv in the layer name. This is convolutional layer. We can get the weight out. Right? Filter and bias, and then print it out. We get the layers and the weight dimension. And we can get the model layer 1. Right? Model layer 1. This is the first layer, and then this is normalization of the filter, and then plot. And here is the layer 1 VGG, which the bright color here indicate the value of 1. The dark would indicate the value of -1. That change in between them, I think. No, -1 and 0, right? Because this is scale of min-max scaling. So this is 0 and 1, low value and high value. So you can see that each of these would detect different patterns. Right? And if we use this to convolute on the first layer, what feature map would we get? We can do this by cut and paste. The cut and paste of the model. So from the model here, you can see that we load the model, and then we will have a bunch of layers. Starting from here, the first index, this is block convolution, block 1 convolution 1 to block 5 convolution 3. We would select the output of block 1 and put it to here, a model interface, saying the input is model.input, and the output here, we reconfigure it to be shortcut, to be just the first, actually the second one. The output of the model layer 1, actually model layer 1 is this one, model layer 1, the output of model layer 1. After the first layers, right, we will get the output of things after the first layer. So then we will see the feature map of the data, and then the summarization of the new configuration will be getting only the first layer, and load the image, load the bird data, and then this is the array of the image with the shape of 224 times 224 times 3. Add another dimension so that we get this shape of 1 in the batch. You need this configuration because Keras requires you to have the first index as the number of samples that you want to work with. Okay, and then pre-process the input, which would scale the image, and then perform prediction to get feature map. And here are the feature maps that are detected. The feature map will be the size of 64 times 64. There are 64 map with the size of 224 times 224. So each of these will show you what are the results of detection at the first stage. What you see here is that some of them focus on the background. Some of them focus on the belly of the bird. Some of them focus on the general outline. Right? Some of them, again, the general outline on the different direction. But you can see that here the feature map demonstrates that the network can learn to detect different patterns. This is the pre-fit VGG. Okay. Let's look at different layers, the results of different layers. This is the layer 2, 5, 9, 13, and 17. Okay. So this is like from the block 1, and then we put it on the block 2 and on the block 3, so that you can see that it kind of detects the higher abstract version of each, and on the block actually not from the block 4, actually it should be from the block of 13 and the block of 17, right? This is the block of the 17 at about the end. You can see that it actually detects the location of different part of the bird. I focus on the head, focus on the foot, focus on the tails, focus on different part of the bird. Right, so this is a way that you can plot the feature map. You can say cut and paste, right? Cut and paste the model to the output, and then use predict to predict the feature map out. Okay, this is all of the convolutional neural network demonstrations. You can see that in order to build one, you just need to configure the convolutional architecture and then train the model, right, enough time so that it fits with the data that you have. Note that you need the data that are quite varied. Right? So the data the test here, they are quite that you have quite a lot of images to work with. If you have like hundreds of pictures, that wouldn't work. Right? You need like 10,000 of them in order to train the network to perform a small task here. Okay, this is the end of today's lecture. Do you have any questions? You can ask me about the assignment as well if you want. And the assignments ask you to build your own convolutional neural network on whatever architecture that you want. You can have like VGG style, you can have like direct style, whatever. I will leave that up to your creativity.